All right, my name is Kosta Derpanis. I'm an associate professor at Ryerson University. Jokingly, sometimes we call it the University in Toronto. We're about 10 minutes away from the University of Toronto. So what I want to talk about today is basically some of my research. So I'll give you a sampling of the type of stuff that we do in my own lab and with collaborators. And then at the end, hopefully I can hold up and I'll have some words about John. So we're in the era of deep learning. Right? This has been a revolution in computer vision, right? But really it's just rebranded neural networks. So what we basically have are high-capacity, nonlinear function approximators. So it turns out that 2012 was a special year, at least in computer vision. This is kind of like the demarcation between, well, I have to be careful, old and new computer vision, okay? So basically, a convolutional network entered the ImageNet competition. So for those that don't know the ImageNet competition, there's about 1,000 categories. It's an object recognition task, and there's about 1 million pieces of training data. So over here, I'm just showing you on the horizontal axis the various years the competition was run, 2010, 2011. Those were handcrafted manners of doing computer vision, or sorry, object recognition. And on the vertical axis, I have the error rate. So in 2012, basically a convolutional network halved the error rate. And ever since then, the error rate has been going down and down and down. And in fact, if we start looking at the number of publications in computer vision, so on the vertical axis, I have the premier conferences in computer vision from 2013 to 2016, and the percentage of, it's an estimate, but the percentage of computer vision papers that use deep learning in some manner. So the year after the ImageNet competition, 2013, very few people were using deep learning. There was quite a bit of disbelief about this thing working. But then, if we start looking at the trend, up to about 2015, there was a large increase in the number of people using deep learning, and then it kind of plateaued. I think the plateau was basically everybody doing object recognition and detection, for that matter, had shifted over, right? But then what happened was people started finding other ways of using these nonlinear approximators. So the trend has been going up and up and up. Is John smiling? Okay, good. Just checking. So this is really a caricature of computer vision. Neural network plus data. Some people believe, definitely not John, or me for that matter, that all we have to do is just make these networks larger and larger and larger. And on the right-hand side, we just need more and more labeled data. But most of us know this is not going to scale up. This might be fine for the low-hanging fruit, but in many problems, we just don't have enough data, nor does the architectures that we use nowadays really match the data that we're actually processing. Right? So over here, I'm just showing you an example. So there's been a trend towards introducing domain knowledge back in. So over here, I'm just showing you work. I really like this work. This is from Bill Freeman's lab. So what they're trying to do here is they're trying to estimate the three-dimensional pose. What you notice over here is they're breaking this up into modules, 4 modules to be exact. And here's the interesting thing. They even have a module that integrates domain knowledge, geometry. So rather than trying to learn it from scratch, they're actually introducing it into the network, because for one thing, they're dealing with the problem of not having enough labeled data. Here's another network. They use some form of attention. John just looked up. Now, whether we agree or not, whether this is the right way of integrating it, as you can see now, people are adding more and more domain knowledge into these networks. So in fact, what I'm saying here is that probably the era of feature engineering is over, but what we've replaced it with is architecture engineering, where the domain expert is playing a large role. So what I want to do next is just share 2 projects from my lab that integrate domain knowledge. So the first one I want to talk about is this work that we presented at ICCV recently, which is segmentation-aware filtering. So what we're doing here is we're actually addressing the basic architecture of the convolutional network for pixel labeling problems. So there's a variety of pixel labeling problems one can address. The problem that we addressed in this paper was the problem of semantic segmentation. So what we want to do here is for each pixel, we want to label it as belonging to one of k categories. So for example, in this scene over here, maybe cow versus grass versus sky. Now, these pixel labeling tasks basically use standard convolutional networks. Over here we have the input, we have the cow image. We take it through a convolutional network, pretty standard from the object recognition point of view. So you can think of this as a feature encoder. And then progressively what happens is there's this decoding stage. So you go from our image to our label map. Right? So essentially what we have here are these repeated convolutions and subsampling, upsampling, depending on whether we're on the encoding or decoding stage. But this network is not without its issues. So what I want to show you is the following. So think of it this way. Here's our input image, and here's our original filter. So our filter is, let's say, 3 by 3. So let's take a look at the next layer. At the next layer, our effective receptive field, basically what our effective receptive field means here is the pixels that it potentially can touch in the original image increases, right? And as we start going up the layers, the effective receptive field gets larger and larger and larger until potentially encompasses the whole image. Now, that might be fine from an object recognition task where we want to label an image as cat, dog, or whatever, but if we're interested in a pixel labeling task, the problem potentially here is we're taking unrelated information and we're mixing it together. Right? So let me just show you here an example. So here's our image, and here's the output of one of the state-of-the-art convolutional networks. This is the Deep Lab network over here. So notice how it kind of gets a sense of there are two cats, but the boundaries between the two categories are quite fuzzy. And the reason being is because we're mixing information from one and the other as we're building this representation. Now, some have actually used a conditional random field. So essentially what they're going to do is they're going to take the output and use a conditional random field in order to sharpen the output in a post-processing task. Now, this post-processing task can be ad hoc, separate from the network, or more recently, people found ways of actually integrating it as part of the network. So basically learning it end-to-end from the output of from the conditional random field all the way to the input. But the problem here is, or at least the way I look at it is, we've already created this problem by this feed-forward process, and essentially what we're trying to do is we're trying to use a CRF in order to fix the problem. So what we're going to do is instead we're going to actually change the architecture in order to avoid this mixing problem altogether, or at least we're going to try to decrease it as much as possible. So let's take a look at our image over here again. What I'm going to do is I'm going to zoom in. So let's consider this pixel over here, and over here I'm just showing you the outline between one category, cat, and the background. And here's my only equation for this whole talk. So basically what we're going to do here is when we're performing convolution, we're going to basically we're actually going to apply spatially invariant filtering. So it's called convolution. In fact, it's actually correlation, but you know, the deep learning people have a habit of renaming things. Nonetheless, so we take a look over here. Here's our mask. So our mask basically straddles both the cat category and the background, and essentially what we're doing here is we're mixing information. So what we're going to do is we're going to change this process slightly. So what we're going to do is we're going to add a mask. And this mask is going to basically be conditioned on what it's looking underneath. Okay, so we basically have an image condition filtering. So rather than basically consider all the information within that convolutional mask, what we're going to do is basically only consider the information that has a high affinity with the point I'm currently looking at. So you can think of this basically as a generalization of a bilateral filter. Okay? So if we look over here now, here's the original output from Deep Lab, state-of-the-art result. Here's the result with our SegAware result. So we're not actually, we could potentially add a CRF on top of this, but notice over here we have no CRF, we're not including the CRF, but yet we get strong boundaries between each of the categories. And what we've done basically is we've avoided the mixing from the get-go. So we've done a lot of quantitative results in the original paper. Here I'm just going to show you some qualitative results. So over here's the input. Here's the output of Deep Lab, the convolutional network. It seemed to do quite well, but the boundaries are quite fuzzy. This is not surprising. And over here we have our result. Okay? Once again, we're trying to avoid the mixing from the get-go. Over here we have the input, sheep. Here's the output. So here we're able to partition sheep versus background. And here's our segmentation aware result. Okay, so notice that the boundaries are they hug quite closely around the objects of interest. And so that was a discrete labeling task, but we've also applied it to a continuous, you can think of it as a continuous labeling task, and that's the problem of optical flow. So over here, I'm just showing you two frames that are being cycled back and forth. Here's the output of FlowNet. FlowNet is another convolutional network that predicts optical flow. And over here's our result by taking the original FlowNet paper, but also including these segmentation-aware layers. So notice how the boundaries are much stronger between the various constituent layers. So here's an interesting paper that just came out about last week. So this is kind of the exciting thing, computer vision. It also can be very tiring. There's so much work coming out literally on a per hour basis. So this actually ended up on one of the blogs, and I looked at it originally and said, wow, that's interesting. And when I started looking at it very closely, they're actually using the same type of segmentation-aware filtering, except they called it, I think, a better name. They called it partial convolution, which I suspect is going to actually catch on much faster than segmentation-aware. But nonetheless, here's the input image, and those white regions are basically holes. And what we want to do is we want to complete this image without knowledge of what's behind there. And here's the output that they get. So they've applied this to a variety of things, not only faces, which tend to be the easier type of things to deal with, but also scenes. So in terms of a summary of this work, what we've done here is we proposed a general image condition filtering layer. It doesn't add too much additional computational cost nor memory. And also, if you take a look at the paper, we actually show strong improvements over a baseline. And the improvements are not only on the final result over the whole image, but they actually appear where they count, around the boundaries. So we've actually measured the performance around the boundaries, which is not standard in this literature. So if you're interested in this, we have a project page. You can take a look at it. Code is available. Okay? So is there any questions regarding this one? Because I'm going to shift on to my second and last project. No? Okay. Okay, so this is very, very recent work. It's actually going to appear at CVPR next month, and that's with my master's student, future PhD student. Look how happy he is right now being a master's student. It's not going to last long anyway. And he's co-supervised with Marcus Brubaker, who's also at York. Okay, so what we're interested in here is we want to synthesize dynamic texture or video texture. So the first question is, what is texture? And what I'm going to do is we're just going to basically take a statistical point of view. Okay, and this goes all the way back to Bella Ulege's work. And what we're going to do is we're going to assume that a texture is something where if we measure the statistics of features at a particular region, so let's say over here, they do not change from one region to another region to another region. Right? And in the case of the synthesis task, what we're going to assume is that if we're able to generate a texture such that the statistics match our target texture, then perceptually at least, they should be indistinguishable from each other. Even though if we look at them from an intensity point of view or a pixel-wise point of view, they will be completely different. Okay, so that was texture. In terms of dynamic texture, we're just going to extend this definition from the spatial domain to the spatial temporal domain. So we're going to assume that the statistics of some features are the same, irrespective of where we measure them, both in space and also across time. Okay, so here's our task. We're given a target texture, and what we want to do is we want to generate another texture. Okay? They're completely different from a pixel-wise point of view. We can actually generate larger textures. But in terms of this synthesis case over here, the statistics of some type of features, and I'll talk about in a second, are indistinguishable. And I think you would agree with me that, at least modulo some artifact, they're quite indistinguishable from the point of view of texture. So this is classic work. So if you take a look at Heeger and Bergen, they talked about basically matching statistics using histograms. Histograms of handcrafted features. In their case, they were using derivative of Gaussian features. Simoncelli then built on top of this work, and he basically added additional statistics in order to make in order to basically increase the spectrum of textures that can be encompassed by this model. And more recently, so this is the work from Gaddis from 2015, what they did was, rather than using handcrafted features or taking statistics of handcrafted features, what they did was basically take statistics from a variety of layers in a convolutional network that was originally trained for object recognition. So what I'm going to do is I'm going to take you through that, because essentially what we're going to propose is a two-stream strategy. Okay? One that's going to model the per-frame appearance, and the other stream that's going to model the dynamics. Okay? So in terms of the analysis stage, what we have is a convolutional network that's been trained for object recognition. So it's being pre-trained for object recognition. So we take our input image here, and what we're going to do is basically measure the statistics of the filter responses at a variety of layers. Okay, so in their case, what they do is they basically take statistics of correlations between filter responses at each of the pixels, and they just aggregate them together. So that's the analysis stage. I mean, this is basically reminiscent of all the classic work. The only difference is, rather than using these localized features, these handcrafted features, what they're using over here are features from a convolutional network. Okay, in terms of the synthesis stage, now what we're going to do is we're going to start with a noise pattern, and we're going to basically cast this as an optimization. So what we want to do is the following. We want to iteratively adjust the input such that the statistics of the final result match the statistics from the analysis stage of our target texture. So over here, I'm just going to show you how we're iteratively adjusting it. Okay? Adjusting the pattern, or the pixel values, in order such that when we put that texture through the network, its statistics match our original target texture. Okay, so that's the appearance side. But what we're interested in is not only the appearance side, which will form one of our streams, but also the dynamic stream. Okay, so what we want to do is we want to measure, or we want to have some way of measuring the statistics of the dynamics alone. Okay? So we're also going to cast this, not surprisingly, as a convolutional network. But what we want are statistics that only focus on the pattern dynamics. We want them independent of the appearance, because we have an appearance stream that will be responsible for just capturing the per frame appearance. So what we're going to do is we're going to go back to some old work. Okay? So what we're going to do is basically recast this convolutional network such that it measures this notion of motion energy, or if you like, spatial temporal energies. So this is also classic work dating back from in the mid-'80s, maybe even earlier, so I don't want to get in trouble with this. Right, and then Simoncelli went and he basically came up with, and I'm not sure what the status is of this, but Simoncelli and Hager basically came up with a computational model of empty neurons, which basically generalized or extended this idea of motion energies. And then with Rick, during my PhD years, we attacked a variety of problems. So the difference between what people were doing previously and what we were doing was we were basically trying to attack a spectrum of dynamics. So not only were we interested in motion, or you can think of basically the pixel-wise translation of, or the apparent translation of intensity, but we were also trying to classify or segment stochastic patterns. Okay? So I won't give you the details in terms of the motion energy computation. Keep in mind that you can actually cast it as basically a sequence of convolutions and nonlinearities. But here I just want to give you a little bit of sense of what we're really measuring when we're measuring the motion energy. So think of this video over here and think about it in terms of a spatial temporal volume. We have two dimensions in space, x and y, but we also have a temporal dimension. So what I'm going to do here is I'm just going to focus basically on that line, on that row, and now I'm going to play the video. So notice here that motions correspond to some type of orientation in the spatial temporal domain. Notice if a pattern is static, then you basically get the vertical lines, and if something is actually moving with some velocity, then that velocity corresponds to an orientation and that volume. And basically what we're doing with these motion energies are we're measuring the presence or the relative presence of particular orientations in that volume. Okay? And in my PhD work, we extended this to dealing with stochastic patterns also. And we were able to show, at least empirically, that this first order analysis was capable of distinguishing both motion, but also stochastic patterns. Okay, so that's the analysis side. So what we're going to do is basically we have an appearance stream and a dynamic stream. Appearance stream, we're going to basically take statistics over a convolutional network that's been trained on object recognition. And in terms of the dynamic stream, we're going to basically measure the Fourier energy. And what we're going to do is the following. We're going to, once again, iteratively adjust the input. But this time around, what we're going to do is we're going to match both the statistics in the appearance channel, but also in the dynamic stream over here. So if you take a look here. So eventually, as this optimization goes on and it takes thousands of iterations, you could actually recast this as a feed-forward network. We haven't looked at that yet. But eventually, you're getting the sense that it both looks like water, but it also behaves like water. So we've performed extensive evaluations on Amazon Turk. So we had about 2,000 subjects, and we basically put them through a forced choice test, which basically said, can you distinguish the real one from the fake one? And we've also have timed experiments, right? So we give them a small exposure time, but we've also tested with long exposure times. And for many textures, especially the ones that basically follow our assumption that the statistics are invariant both spatially and temporally, then for very small exposures, we're basically at chance in terms of distinguishing. Of course, as the amount of time or the amount of exposure time increases, subjects get better and better in distinguishing them, and I suspect part of that has to do with artifacts in our synthesis. Okay, so it's quiz time. So what I'm going to do now is I'm going to show you two textures, and I want you to tell me which one is the real one and which one is the fake one. So what I'm going to do is I'm just going to ask you which one the real one is, and I'll give you a couple seconds and just scream it out which one you think it is. Okay, here you go. Which one is it, left or right? Is the real one? Left. Okay, so we fooled at least one. Okay, so the real one is indeed on the right-hand side, the fake one. But if you start looking closely, you start noticing little artifacts. We haven't bothered post-processing this. Okay, so that's something to keep in mind, and there's other improvements that we can make. But I think you get a sense that it kind of looks like these school of fish, both in terms of appearance, but also in terms of its dynamics. So here's another one. So here's the target, and we want to synthesize more of this type of stuff. So here's a synthesis one, or the generated one. Here's another one. Here we have these flying birds. So that's a target, and that's a synthesized one. Okay? So over brief exposure times, I would claim it's very difficult in order to distinguish. As you get more time, then you can start noticing artifacts and things like that. Okay, so here's why we went two-stream. And so you could potentially, and other people have looked at one stream, they're basically going to treat the video as a spatial temporal volume and try to get these joint statistics. Here what we want to do, the reason we wanted to factor it, because what we want to do is we want to mix different appearances and different dynamics from different sources. So over here we have our source appearance, it's some painting. And over here we have the dynamics. These are real. Okay, dynamics from one. And now what we want to do is we want to take the dynamics from the right, we want to take the appearance from the left, and combine it together and get something like this. Okay? So here's another one. This one's one of my favorite. Actually, this is my favorite. So we want to take the appearance from the left, and we want to get the dynamics from the right. We want to combine them together and get the following. Okay? So it's still a work in progress, but Matthew is very artistic. It's something that he wants to push forward, and maybe you can talk to Dimitri later and figure out how we can get a SIGGRAPH paper. Okay, there's a lot of work to be done. Anyway, in terms of summary, what we do is we propose a novel two-stream method for synthesizing dynamic textures, and we've validated the model on a large-scale evaluation, okay, using human observers. If you're interested in this project over here, we have a project page for this one also. It also includes code, so the code's being released. I think that's a story that I would tell all graduate students is make sure you release your code. Otherwise, out of sight, out of mind. So if you want people to really cite your work and really use your work, you should make the code available. Okay? Okay, that's enough about me. Now it's about John. I met John in 1998 at the University of Toronto. At the time, I was a third-year undergraduate student. Completely lost, to be honest with you. I mean, we were part of the dot-com generation where we thought we'd be millionaires by the age of 25, building, out of all things, web pages. And it just happened, I was in my algorithms course, and I was just sitting with a friend, and I said, my only experience is at my dad's restaurant. I really need experience, and I go, where have you gotten experience? Well, I worked with a professor over a summer. I go, what do you mean? We did research. And I go, what is research? I said, I just don't want to hear it. Just take me to your leader. Let me meet John, right? And, I was John's summer intern, and then that turned out to be a 2-year full-time research assistant. And after that, I was co-supervised John in terms of my master's thesis. So what I want to do is I want to conclude with a few words about John. So I should have done what Sven did because I don't know if I'm going to make it through it, but I should have written this down. But anyway, let's see here. So the first word is role model. Okay, so role models are important. We're in the age of equity, diversity, inclusion. We all talk about role models. And, let me just step back. I am a first-generation Canadian. My parents came from Greece. They had very little education, and they were great role models in terms of hard work. They valued education. They gave me the money, whatever you need, tutors and this. But, there was a ceiling at some point. And then, I saw John. One of us, right? Someone that, started as a first-generation Canadian, worked hard, worked up the ranks, and it can be done, right? So, having role models, having examples, I really value, and that's just one of many facets of John being a role model. The second one is opportunity. I remember when I first met John, it's like yesterday, where John goes to me, so I would like to be your summer intern. And John said, are you any good? I think so. And he goes, I don't have any money right now. I said, don't worry about it. I need the experience. Okay, no problem. Show up next week. I show up next. By the way, I have money. He goes next week. Great. But, it's not only me. There's so many people in this room and elsewhere that have gotten their first start with John. Opening up his doors, giving people first chance, just giving a taste of research, and it's something that I've highly valued in my own lab. So I take in 2 or 3 undergrads every year with no expectation, to be honest with you. It's a learning experience, and I hope they get something out of it. I don't expect, something in return, right? It's kind of like paying it back, for all those years that, John gave me a chance. And the final one is a friend. So I've been very fortunate to have awesome advisors. And, from time to time, I get into trouble or I need advice. John's one of the first people I call. What do you do in this situation? This is where I'm at this way. And John's made a tremendous amount of time. He's pulled me off the cliff many times when I wanted to go one direction. He said, think about it clearly because this, and this. So, they say advisors are there, partly for the intellectual part, but also partly for the emotional part. And, John's been a great friend all these years, and thank you very much, John. That's it.